Assalamualaikum warahmatullahi wabarakatuh and good afternoon. We are from Group K2 Final Year Design Project. So our title for this project is Production of Oleic Acid from Olive Oil. My name is Muhammad Rizwan Lubis. Together with me today is Tio Ziling, Nurul Shafiqah and also Siti Nurdiana.
From our previous presentations, we have received some suggestions from the assessor and we have taken the improvement. The action taken is such as add another absorption column into the process. We have been using standard A for the waste management based on the location of the plant, and we also state the type of the process unit based on the PFD. And then for the solution for the main valve fail, we have taken the action by using bypass valve as a backup for the main valve as stated in the hazard.
For the introduction, the theme for this year is production of raw material from renewable resources for non-alcohol-based hand sanitizer. Therefore, our title is Production of Oleic Acid from Olive Oil, where our renewable raw material is crude olive pomace oil, where oleic acid can be used as excipient in pharmaceutical and as an emulsifant in hand sanitizer, where emulsifant in hand sanitizer can thicken the hand sanitizer into a gel. The table below shows the composition and function that have enhanced resin, where oleic acid can be used as antimicrobial agent, humectant and thickener in hand sanitizer. And the reaction below is showed is the main reaction for the production of oleic acid, where our plant capacity is 31,200 kg per day, which fulfills 6% supply deficiency, 1.9% global demand, and 2.9% global supply.
We start off with a conceptual design where we have selected the type of process to be used for our production. Colgate Emery process is being selected for the production of oleic acid, where this process will utilize high temperature and pressure, which allow a high degree of hydrolysis without the use of catalyst. So for our production, hydrolysis reaction will take place at high temperature and pressure, which is 250 degrees Celsius and 15 bar without the use of catalyst. So the diagram here shows the overall input and output diagram for the production of oleic acid. The process unit will be involved in our production will be reactor, flash column, extraction column, distillation column, and adsorption column. And the main process, which is the hydrolysis reaction, will be an endothermic reaction. Before we proceed, we consider the future economic potential, where we'll consider the cost of material, the cost of reactor, and cost of separation unit. And finally, we get the future economic potential to be 2.78 million.
Next, we move to the process description. So the main reaction that occur in this production is hydrolysis reaction that will operate at 250 degrees Celsius and 15 bar of operating pressure, which is it will take place in CSTR R101. So as we can see here, the olive oil and water will be our raw material that will produce oleic acid and glycerol. At the downstream process, we will involve a few series of separation unit to increase the purity of our product, which is flash column, extraction column, distillation column, evaporator, and also adsorption column.
Next, for the plant location, based on our plant design, 5 locations are chosen for the consideration, which is at Chukai Terengganu, Butterworth Penang, Pasir Gudang Johor, Kuantan Pahang, and Tanjung Kupang Johor. The table shows the characteristic of each location, and the next table shows the mark analysis, which is used to assess the location. The final decision is based on the total mark calculated as shown in the table, and Pasir Gudang Johor is selected as the most ideal location for the proposed for the plant. Based on the above mark analysis, Pasir Gudang is chosen due to the reliable raw material, acceptable land price and area, infrastructure, and availability of labor. The proposed plant location at Pasir Gudang Johor is shown as in figure. Next, for plant layout, by referring to guideline for seating and zoning of industry from the OE, for the safety purpose, the control room are located adjacent to the process unit but with potentially safer distance from the hazardous process such as at reactor. And then the wind direction will be considered from west to east for the installation of hazardous unit operation. In addition, based on the process requirement, the arrangement of the unit operation and then the piping is minimized. The plant layout drawing is as shown in the figure.
Next, we move to profit analysis. The total capital investment for this project is around 100 million ringgit. For the total product cost as calculated is around 89 million ringgit. The return of investment was calculated by considering 20% of MARR, so that the return of investment will be around 33%. Therefore, this project is said to offer an acceptable return. Furthermore, the payback period for this project is 2 years with reference of 4 years. The net present value for this project is 74 million ringgit with 34% of interest rate. For the break-even analysis, from the first graph we can observe that the break-even point for this project is at the first year of the production. Next, from the second graph, the break-even point for production capacity is 4,800 tons per year. Thus, this plant is favorable since the production capacity is larger than the break-even point. Next, from the third graph, we can see that the production plant start gaining the profit at 5th year of the production, since the cumulative cash flow started to show the positive cash flow during that time.
For safety issue part, we have identified the legislative requirement related for our operation. Then we have identified the hazard for our operation and further study on the hazard case study related. Hence, in order to prevent the accident and hazard from happening, we have applied hazard system, hazard, and higher in our production.
For waste management part, for production, the waste generated is water that contains folic acid and glycerol. So this is a wastewater treatment plant for our production where we use activated sludge, acidification and coagulation method to treat the water before it is being discharged. So from the initial COD and BOD, after each treatment, the COD and BOD will be reduced to 77.72 mg per liter for COD and BOD will be 19.91 mg per liter, which is below the standard B set by the Environmental Quality Act. So this is the PFT for the production of oleic acid. After we have determined the pinch temperature hot stream, cold stream after heat integration, this is the PFT after heat integration and the total energy recovery is 50%.
Next, we move to PID. So this is our PID before considering HAZOP. We can see here some control systems are applied such as temperature controller, pressure controller, and flow rate controller. After considering HAZOP, we apply the alarm system and bypass to improve the safety aspect and reduce the operational risk. Okay, now we move to detailed design and mechanical drawing that we have done individually, where in this section will be presented by me, Siti Noriana, Nur Shafika, and also Teo Zili. So we start with continuous third tank reactor R101 that will present by me, Muhammad Rizwan Lubis bin Fahrudin Lubis. So this is the block diagram of reactor R101. So there are 2 inlet and 1 outlet as shown in this diagram. So next we move to the detailed design of the reactor. The diameter of this reactor is 3.25 meter with height of 6.5 meter. So the baffle section, impeller section, and also jacket section also been calculated in this section. Next, for the mechanical design of the reactor, the material of this construction is austenitic stainless steel 316 with the internal diameter of 3.25 and thickness 30 mm. The type of vessel support is skirt support with 50 mm of thickness, and the type of flange is welding neck flange. Next, as we can see at the left side of this drawing, show the overall view of CSTR R101, while on the right side show the cross-sectional view of manhole, neck flange, and also skirt support. So this CSTR will operate at 250 degrees Celsius and 16 bar of operating pressure. So as you can see at the table below, show the design of flange and manhole size, and also the type of flange that been used, which is welding neck and also blind.
For the mechanical part of evaporator, I am Shavika will explain the mechanical design for the evaporator. This is the block diagram of evaporator where in the evaporator they have 1 inlet and 2 outlet for the evaporator. And this is the summary design of evaporator where the operating temperature is 110 degrees Celsius, the operating pressure is 101.325 kPa which is equivalent to 1 bar, and material of construction is stainless steel where the vessel height is 6.8 and the effective length is 6.29 and the vessel wall thickness is equals to 9. For the mechanical drawing, this is drawing that has been drawn in the AutoCAD, where in the drawing there is top view vessel, skirt, and the flange, as well as the standard dimension for the flange. And in the left hand side, there is been the design specification for the mechanical drawing.
I'm Gilziling. I'll be presenting about the design for distillation column D101. So, this distillation column is used to separate the hexane being used from the feed inlet of the distillation column. Oleic acid, triolene, and hexane will enter the distillation column, and the distillate will be hexane, which is way more volatile than oleic acid and triolene. Distillation column D101, as you can see from the left, is the overall view of the distillation column, while on the right side shows the design of some parts of the distillation column, such as the tray, the base ring, the flange, and the skirt. So this distillation column will be operating at a temperature of 85 degrees Celsius and a pressure of 3 bar. So the MAWP vessel will be 12 bar. And the total height of the column will be 12.48 meter with a diameter of 1.67 meter. So there are 3 main holes, 3 inlets, and 2 outlets on this distillation column. And the skirt height will be 1.5 meter. So the safety factor being considered for this distillation column is 10% and with a corrosion allowance of 2 mm. There are 14 stages in this distillation column, with the type of tray is sieve tray. The type of head used for this distillation column is Torus spherical head. There are 2 types of flange used on this distillation column, which is welding neck flange used for the inlet and outlets, and the blind flange is used for the main hole. The type of material used for this column is authentic stainless steel type 316.
I am Siti Nordiana and I will explain about the detail and mechanical design at absorption column. So basically, this is the block diagram of absorption column, which consists of 2 inlet and 2 outlet. So in our plant, 2 similar absorption column will be fixed in the plant to operate alternatively, besides to ensure the continuous process during the maintenance. So from my calculation for the detailed design and mechanical design of absorption column, the absorption column is designed with a vertical layout with 2 1-ellipsoidal head at the top and at the bottom. By considering the internal pressure for absorption column, the mechanical is calculated for the conditions that are needed for the design have been calculated. The condition for the design of absorption column have been summarized as shown in the slide. The operating temperature will be 40 degrees Celsius and the operating pressure is at 1.5 bar. And then I'll be using stainless steel type 304 for the material of construction. And the column diameter will be 2.13 meter and the height of the column will be 6.4 meter. And then the type of vessel support that I'll be using is the skirt support. So basically, this is the mechanical drawing for absorption column. It's shown the view of top view, front view of the skirt support, cross-sectional view of flange, cross-sectional view of the column, and also the cross-sectional view of the main hole. As a conclusion, oleic acid produced from olive oil can be used as thickener in hand sanitizer. And based on the supply and demand, the plant capacity we have been set at 1,300 kg per hour. And then the conceptual design is made before proceed to the process flow diagram and piping and instrumentation diagram. High rate and heads up are done to eliminate the possible hazard. And then for the mechanical drawing of reactor, evaporator, distillation column, and absorption column are shown with the detailed design for each unit by considering from the various perspectives and with the justification and the calculation. Thank you.